If you have ever looked at two world maps and felt like the continents were changing shape, you were not imagining it. They were. A map projection is the mathematical process that converts positions on Earth's curved surface into positions on a flat page or screen. Earth is roundish, a plane is flat, and that mismatch creates a hard geometric problem. The key idea is simple but unavoidable: there is no way to flatten a sphere without distortion. So every map is accurate in some ways and inaccurate in others. That is not a design mistake, it is the entire game of cartography. When people say a projection is wrong, what they usually mean is that it is wrong for the purpose they have in mind. A navigation chart, a classroom political map, and a climate data visualization can all require different priorities. Projection choice is less about finding perfection and more about choosing which truth matters most for your task. At a technical level, map projection starts with geographic coordinates, usually latitude and longitude. These coordinates identify a location on Earth's surface. A projection applies formulas that transform those spherical coordinates into planar x and y coordinates. That transformation can be smooth and continuous, but it cannot preserve every geometric property at once. Cartographers usually evaluate projections by how they treat four things: area, shape, distance, and direction. Preserve one perfectly and you generally sacrifice one or more of the others. This trade-off is not a bug in specific formulas, it follows from deeper geometry. In practice, projection design is a controlled compromise. You decide what users need to read from the map quickly and reliably, then choose a projection that protects that information while accepting tolerable distortion elsewhere. So projection is both mathematics and communication design, because the chosen distortion teaches viewers what to notice first. To understand distortion, imagine drawing a tiny circle on a globe around each point. After projection, those circles become ellipses with different sizes and orientations. That thought experiment, formalized in tools like Tissot's indicatrix, reveals exactly how local scale and shape are altered from place to place. If the tiny circle stays circular, local angles are preserved and the projection is conformal. If the circle changes size differently across regions, area and distance are being stretched unevenly. This matters because our brains interpret map geometry as factual geography. We infer relative importance from size, proximity from distance, and strategic alignment from direction. Distortion therefore has social and analytical consequences, not just aesthetic ones. A projection can unintentionally overemphasize high-latitude regions, compress equatorial zones, or make route planning seem more intuitive than it is. Once you see distortion as structured and measurable rather than random, projections stop feeling like competing opinions and start looking like different instruments calibrated for different jobs. Conformal projections preserve local angles and shapes at very small scales, which is why they have long been favored for marine navigation and some engineering tasks. The most famous example is the Mercator projection. On Mercator, rhumb lines, routes of constant compass bearing, plot as straight lines, making manual navigation calculations practical in the age of sail. That practical advantage explains Mercator's historical dominance far better than any claim of visual neutrality. But conformality comes with a cost. Area inflation increases dramatically with latitude. Regions near the poles appear far larger than they are relative to equatorial areas. Greenland can look comparable to Africa in many wall maps, even though Africa is vastly larger. So Mercator is excellent for preserving local angles and directional consistency in certain contexts, but deeply misleading for visual comparisons of size. Criticism of Mercator is really criticism of using a specialized navigation projection as a general-purpose worldview map. Equal area projections flip that priority. Their central promise is that any region's displayed area is proportional to its true area on Earth. That makes them useful for comparing land extent, population distributions normalized by area, ecological zones, and resource maps where scale honesty matters. Projections like sinusoidal and Gall-Peters are common examples in public debates because they visibly correct the high-latitude inflation seen in Mercator. But equal area does not mean shape accurate. Continents can appear stretched, squashed, or elongated in ways that feel unfamiliar, especially near map edges or at high latitudes. People often interpret that unfamiliarity as inaccuracy, when in fact it is the opposite trade-off: area is right, shape is sacrificed. For thematic mapping, this can be exactly what you want. If your message depends on fair comparison of territorial magnitude, equal area projections prevent the visual bias introduced by area distortion, even if coastlines look less like the classroom map many viewers grew up with. Then there are equidistant and azimuthal families, which preserve selected distances or directions from specific points or along specific lines. These projections are often misunderstood because the word equidistant sounds absolute. In reality, distance accuracy is usually conditional, true from one center, or along one set of meridians, not everywhere on the map simultaneously. That still makes them extremely useful. Air route maps, radio range charts, and polar logistics often rely on projections that keep great circle relationships readable from operational hubs. Azimuthal projections can preserve true direction from the center, helping users reason about bearings across large spans. Again, purpose defines value. A projection that looks strange for global political education can be ideal for communication networks or emergency planning centered on one region. The lesson is that projection properties are local and rule-based, not universal quality scores. Asking whether a map is good without asking good for what is the fastest way to misunderstand cartographic design. Because single property projections can look extreme, many modern atlases and media outlets use compromise projections. These do not preserve area or angles perfectly. Instead, they distribute error to create a balanced overall impression. Robinson and Winkel Tripel became popular precisely because they reduced the most visually jarring distortions while avoiding dramatic exaggerations at map edges and high latitudes. National Geographic's shift toward Winkel Tripel signaled a practical editorial philosophy: prioritize a map that looks globally fair and readable to broad audiences over one that optimizes a single geometric property. Compromise projections are not mathematically pure in the way conformal or equal area systems are, but they often perform better for general reference and storytelling. They help viewers maintain intuitive continent recognition while limiting gross misperception of relative scale. In short, compromise maps are communication tools tuned for mixed objectives, where cognitive clarity and visual balance can matter more than strict preservation of one metric. Projection choice becomes even more important in data visualization and policy communication. Suppose you map deforestation, conflict intensity, disease incidence, or internet infrastructure by country. If your projection inflates some regions, visual weight shifts before a viewer reads a single label. That can subtly alter perceived urgency, fairness, or geopolitical centrality. In scientific and statistical contexts, this is not just style, it can shape interpretation quality. A responsible workflow therefore links projection to analytical intent. If area-normalized comparisons are central, start from equal area. If preserving local form for urban morphology is key, consider conformal regional systems. If routing and direction matter, optimize for those metrics. Also pay attention to map extent. Global, continental, national, and city maps behave differently under the same projection family. Good cartographers document these choices so viewers understand what is preserved and what is distorted. Transparency about projection is part of data ethics, not an optional footnote. Another overlooked point is that Earth is not a perfect sphere. It is closer to an oblate spheroid, slightly flattened at the poles. High-precision cartography and geodesy therefore distinguish between a reference ellipsoid, a geodetic datum, and the projection itself. In everyday world maps, this difference may seem minor, but for surveying, navigation systems, and engineering, it is critical. A projection formula can be applied to spherical or ellipsoidal models, and results differ. Add datum transformations, and coordinate consistency across datasets becomes a non-trivial problem. This is why GIS professionals treat projection metadata as mandatory, not decorative. Without correct CRS information, layers can misalign, distances can be miscomputed, and analyses can fail silently. So projection literacy is not only about recognizing distorted country shapes on posters. It is also about understanding the computational chain that turns Earth measurements into map products you can trust for real decisions. Historically, projection debates are also debates about power, education, and worldview. The map that dominates classrooms and media becomes the map people mentally treat as normal. When that default exaggerates some regions and minimizes others, it can reinforce distorted intuitions about scale, influence, and importance. Critics of Mercator in the 20th century were not just arguing geometry, they were challenging the social effects of a projection used outside its intended purpose. Defenders often replied, correctly, that every projection distorts something. Both points can be true. The productive response is not to search for one morally pure projection, but to match projection to context and to teach viewers what trade-off they are seeing. In education, showing multiple projections side by side can build this literacy quickly. Once learners understand that maps are choices, not mirrors, they become less vulnerable to unexamined visual assumptions and more capable of reading geographic information critically. So how should you pick a projection in practice? Start with the question your map must answer. If the audience compares territorial magnitudes, pick equal area. If they navigate or need local angular fidelity, pick conformal. If the map is a broad reference for non-specialists, consider a compromise projection with balanced global appearance. Next, constrain by extent. For local maps, many distortions are small and regional projected systems can be highly accurate. For world maps, trade-offs become unavoidable and highly visible. Then test readability. Are labels stable, coastlines recognizable enough, and distortions aligned with purpose? Finally, disclose your projection and why you chose it. That one sentence can prevent major misinterpretation. The most honest map is not the one claiming objectivity, it is the one explicit about its design logic. Once you adopt that mindset, map projection stops being an obscure technical footnote and becomes central to truthful visual communication about our planet. If you found this helpful, please like this video and subscribe for more explainers.